Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that goes over ionic compounds, Lewis structure, Vesper theory, valence bond theory, and molecular orbital theory. Let's go ahead and get started with problem number 1. Problem number 1 says rank the bonds from least to most polar. We have boron bonded to oxygen. We have carbon bonded to nitrogen, and we have beryllium bonded to fluorine. When ranking these bonds from least to most polar, the key concept we need to focus on is electronegativity difference. The greater the difference in electronegativity between two atoms, the more polar the bond is. A bond with a very small or zero electronegativity difference is considered nonpolar, while a bond with a large electronegativity difference is highly polar, meaning that the electrons are more strongly pulled towards the more electronegative atom. So to solve this problem, we just need to calculate the electronegativity difference for each bond and then rank them accordingly. Here we see a table of the electronegativity values for elements in period 1 and 2. Let's start with boron bonded to oxygen. Oxygen has an electronegativity value of 3.5, and boron has a value of 2. 3.5 minus 2 is equal to 1.5. Then we want to do the same for the carbon bonded to the nitrogen. Nitrogen has an electronegativity value of 3, and carbon has an electronegativity value of 2.5. Their difference is 0.5. Finally, we have beryllium bonded to fluorine. Fluorine has an electronegativity value of 4, and beryllium has an electronegativity value of 1.5. Their difference is equal to 2.5. Now that we've calculated the polarity of each bond, we can go ahead and arrange them from least to most polar. The carbon-nitrogen bond here has the smallest electronegativity difference of 0.5, so it is the least polar. Then the boron bonded to the oxygen, it has a larger electronegativity difference of 1.5, so it is more polar than the carbon bonded to the nitrogen. Finally, beryllium bonded to fluorine has the largest electronegativity difference, an electronegativity difference of 2.5. That makes it the most polar. So if we were to order them from least to most polar, it would be carbon bonded to nitrogen, followed by boron bonded to oxygen, and finally beryllium bonded to fluorine. So the correct answer here is going to be B. The second problem says, which name does not have the correct formula? When determining whether a chemical formula correctly corresponds to its given name, the key is to check that the charges of the ions balance properly to form a neutral compound. So let's go through each option and verify the correctness of the formulas. Answer choice A says strontium sulfide. Strontium is an alkaline earth metal, meaning it has a +2 charge. Sulfide is a monatomic anion with a -2 charge. Since the charges cancel out, we just need a 1-to-1 ratio of strontium to sulfide. So the correct formula for strontium sulfide is SRS, which is what's given in this answer choice. So this pairing is correct. B says magnesium chloride. Magnesium is also an alkaline earth metal, so it carries a +2 charge. Chloride is a polyatomic ion with a -1 charge. To balance the charges, we need 2 chloride ions to neutralize the +2 charge from magnesium. And we can determine this also by just swapping the charges for ratios. So magnesium 1, which we will not explicitly write, and then ClO2, and this is going to be 2 of these chlorite polyatomic ions. What we see here is a correct pairing of name to chemical formula. So B is also correct. C says calcium carbonate. Calcium is a alkaline earth metal as well, so it has a +2 charge. Carbonate is a polyatomic ion with a -2 charge. Since the charges balance out naturally in a 1-to-1 ratio, the correct formula is going to be calcium, Ca, carbonate, CO3. So this is also a correct pairing of name to chemical formula. Finally, in answer choice D, we have aluminum hydroxide. Aluminum has a +3 charge, and hydroxide is actually a polyatomic ion with a -1 charge. When we crisscross these charges to get the ratio, we're going to have aluminum 1, which we're not going to explicitly write that 1, and then OH3. We need 3 hydroxide ions to neutralize the +3 charge from aluminum. So that means the correct formula should be aluminum and then hydroxide, 3 of them. This doesn't match what's provided in this answer choice. So this is an incorrect pairing. Since we're looking for which name does not have the correct formula, D is going to be the correct answer for problem 2. Problem 3 says, which of the following has the largest lattice energy? Lattice energy is a measure of the strength of the ionic bonds in a crystalline solid. It depends on 2 key factors. The first factor is the charge of the ions. Higher charges on the ions lead to stronger electrostatic attraction, which increases lattice energy. The other factor is the size of the ions. Smaller ions allow for a shorter bond distance, which also increases lattice energy. So the first thing we want to do when we're comparing different compounds and their lattice energy is we want to compare charge. So we look at option A, we have calcium oxide. Calcium oxide has a +2 charge, and oxide has a -2 charge. If we multiply the absolute values of these 2 charges, we get 2 times 2, which is equal to 4. Then we have potassium sulfide. Potassium has a +1 charge, and sulfide has a -2 charge. When we multiply the absolute values of these numbers, we get 2. Then we'll do the same for magnesium oxide. Magnesium has a +2 charge, and oxide has a -2 charge. The multiplication of the absolute values gives us 4. Finally, we have potassium chloride. Potassium has a +1 charge, and chloride has a -1 charge, and the multiplication of the absolute values gives us 1. From here, we can tell that calcium oxide and magnesium oxide, they have the highest charge density. Now, between the two, we need to figure out which one has a higher lattice energy. So from the first step where we compare charge, we know that calcium oxide and magnesium oxide have stronger electrostatic attractions than potassium sulfide and potassium chloride, meaning they are the 2 ionic compounds with higher lattice energy. Now, between the two, we need to figure out which one reigns supreme. So in order to do that, we need to compare ionic size to determine which has the highest lattice energy. For here, we need to remember that smaller ions allow for a shorter bond distance, which also increases lattice energy. Between magnesium and calcium, magnesium is smaller than calcium, which means that magnesium oxide has the highest lattice energy, making option C the correct answer. Problem 4 says, how many atomic orbitals on a carbon atom are required to form the hybrid orbitals needed for bonding in carbon dioxide? In order to solve this problem, the first thing we want to do is draw the Lewis structure for carbon dioxide. Our rule for drawing Lewis structures is first to figure out the total number of valence electrons that we have. We get 4 from carbon, and we get 6 from oxygen, and there are a total of 2 oxygen atoms. 4 plus 12 is equal to 16, so we have 16 valence electrons. Then we need to decide what our central atom is. It needs to be the least electronegative atom. That's going to be carbon. So the oxygen atoms are going to surround the carbon atom. We're also going to form a single bond between each carbon and oxygen. Now we've accounted for 4 out of our 16 valence electrons by forming these single bonds between the carbon and each oxygen atom. That leaves us with 12 more valence electrons to distribute. We'll start by distributing them to the terminal atoms first to make sure each terminal atom satisfies its octet. In order to do that, we're going to give each oxygen atom 3 lone pairs. When we do that, we have now accounted for all 16 valence electrons. But there's a serious problem. Our carbon atom does not have a full octet. In order to remedy this problem, we're going to have each oxygen donate a lone pair and form a double bond between the carbon and oxygen atom. And that gets us the following structure for carbon dioxide. Carbon dioxide has a linear structure with 2 double bonds between carbon and oxygen. To predict the hybridization of carbon, we need to count the number of electron-rich regions around it. Carbon is surrounded by 2 regions, 1 for each double bond to oxygen. So if we have 2 electron-rich regions, our hybridization is going to be sp. To form sp hybridization, that means we're going to take an s orbital and 1 of the p orbitals, and they're going to be hybridized to give us sp hybrid orbitals. So we need 2 atomic orbitals to form the sp hybrid orbitals, which means the correct answer is B. 5 says, how many pi bonds are found in C2H4? Our first step for this is to draw out C2H4, which is shown here. And we notice that there is a double bond between the 2 carbon atoms. And each carbon atom is also attached to 2 hydrogens. Each of the carbon-hydrogen bonds is a sigma bond. So there's going to be a total of 4 sigma bonds from the 4 carbon-hydrogen bonds that we see here. Then from the double bond between 2 carbons, this is going to consist of 1 sigma bond and 1 pi bond. So in total, there are 5 sigma bonds in this molecule and 1 pi bond. Since the problem is only asking for the pi bonds that are found in C2H4, that's going to be 1, so the correct answer is B. Now we move on to problem 6. Problem 6 says, which of the following contains a central atom that is sp2 hybridized? To determine which of the given molecules contains a central atom that is sp2 hybridized, we need to analyze the number of electron-rich regions around that central atom. Hybridization is determined by counting the regions of electron density around the central atom. And if there are 3 regions of electron density, then the central atom will be sp2 hybridized. I have here drawn structures A, B, C, and D. And all we have to do is investigate the central atom in each of these Lewis structures for A, B, C, and D. If there are 3 regions of electron density around the central atom, then it is going to be sp2 hybridized. Let's look at answer choice A. The central atom here is carbon, and we notice that it's surrounded by 2 regions of electron density. That means it's going to be sp hybridized. That's not what we're looking for. Now let's look at B. The central atom here is oxygen, and it's surrounded by 4 electron-rich regions. That means the oxygen atom here is sp3 hybridized. That's also not what we're looking for. Now let's look at structure C. We have our central atom here, which is bromine. It's surrounded by 5 electron-rich regions. That means it's going to be dsp3 hybridized. This is also not what we're looking for. Then finally, for D, we're going to draw one of the 3 resonance structures that we can for the carbonate polyatomic ion. And we notice that the central atom here is carbon. It's surrounded by 3 electron-rich regions, which means the carbon atom is going to be sp2 hybridized. The correct answer is D. Problem 7 says, according to valence bond theory, which orbitals on oxygen and fluorine overlap in the OF2 molecule? This problem is actually really interesting. The first step is to identify the hybridization of oxygen. Since oxygen is bonded to 2 fluorine atoms and it has 2 lone pairs, that gives it a total of 4 regions of electron density. This means that the oxygen atom is going to be sp3 hybridized because 4 electron domains correspond to sp3 hybridization. Next, we consider the fluorine atom. Now, each fluorine has valence electrons in the 2s and in the 2p orbitals. But since fluorine forms a single sigma bond with oxygen, it actually contributes one of its p orbitals for bonding. In this case, the p orbital from fluorine overlaps head-on with the sp3 hybrid orbital from oxygen to form that single bond. So that means the correct answer here is C. sp3 on the oxygen overlaps with 2p on fluorine. Problem 8 says, for which of the following molecules is the indicated type of hybridization not appropriate for the central atom? So here we have A, B, C, and D, and I went ahead and drew the Lewis structures for each for sake of time. This can be good practice for you to attempt to draw these on your own and see if you can get the same correct Lewis structure. Now, A says beryllium chloride is sp2. When we draw beryllium chloride, we see that beryllium has 2 regions of electron density around it. That means it's going to be sp hybridized, not sp2. So that means this is an incorrect assignment. B says we have silicon and it's attached to 4 hydrogens via single bonds. That means it has 4 electron-rich regions around it, and this corresponds to sp3 hybridization. So this is a correct assignment. C is BF3. So we have a boron atom in the center. It's attached to 3 fluorine atoms. That means it has 1, 2, 3 regions of electron density. It's going to be sp2 hybridized. So this is a correct assignment as well. Finally, we have C2H2 that's drawn right here. And we'll notice that each carbon atom here is surrounded by 2 regions of electron density, which means they are sp hybridized. So this is a correct assignment as well. The only pair that is an incorrect assignment is going to be A. This is not sp2 hybridized. It's in fact sp hybridized. Let's move on to problem 9. Problem 9 says how many pi and sigma bonds are in the following compound. To solve this problem, we need to recall that sigma bonds are the first bond in any connection between 2 atoms, while pi bonds arise from double and triple bonds as the second and third bonds. So we're going to start by counting all of the sigma bonds in the molecule. Each single bond is a sigma bond. And then for double and triple bonds, only one of the bonds is a sigma bond, while the remaining are pi bonds. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 sigma bonds. Now we can account for pi bonds. So the remaining bonds are going to be pi bonds. So here where we have a double bond, one of them is sigma, but the other one is a pi bond. Same goes for this double bond right here and this double bond right here. Then for triple bonds, one is a sigma and then the other 2 are pi bonds. So we have a total of 5 pi bonds. In short, we have 19 sigma bonds and 5 pi bonds. So that means the correct answer here is going to be C. Problem 10 says, which of these elements would most likely exhibit hypervalency for bonding? To solve this problem, we need to remember that hypervalency refers to atoms that can expand their valence shell for bonding. So we know that elements in period 3 and beyond can actually expand their octet because they have available d orbitals that can accommodate additional electrons. So keeping that in mind, let's analyze the answer choices. Answer choice A is beryllium. This is in period 2 and it cannot expand its octet since it does not have accessible d orbitals. Same goes for boron. In fact, beryllium and boron are considered hypovalent because they are satisfied with less than an octet. Then we have sulfur. Sulfur is in period 3, meaning it has access to d orbitals and it in fact can expand its valence shell. It's going to be the correct answer for this problem, but we're still going to work through D. D says neon. Neon is in period 2, and it's also a noble gas that already has a full octet. So it typically doesn't form bonds, and it cannot expand its valence shell. So once again, the correct answer for 10 is C. Problem 11 says, how many electron pairs are shared between the carbon atoms in C2H4? In C2H4, the 2 carbon atoms form a double bond, meaning they share 2 pairs of electrons. So the correct answer here is going to be C. Problem 12 says, draw the best Lewis structure for the ion, SF3, and it has a +1 charge. What are the actual bond angles in this ion? So to draw the Lewis structure, we need to know the total number of valence electrons. We get 6 from sulfur, and we get 7 from fluorine, and there's a total of 3 fluorine atoms. 21 plus 26 is equal to 27. But this ion has a +1 charge, meaning it has lost an electron. So there's a total of 26 valence electrons. Then we need to figure out what our central atom is. That's going to be sulfur because it's less electronegative than fluorine. The 3 fluorine atoms are going to surround this central atom, and we can form single bonds between each fluorine and the central sulfur. This accounts for 6 out of our 26 valence electrons. Now, for the remaining valence electrons, we're going to start by distributing them to the terminal atoms to ensure they have a full octet. So each fluorine atom is going to get 3 pairs of lone pairs. Now we've accounted for 24 out of our 26 valence electrons. Those last 2 are going to go on the central sulfur atom. From here, we need to determine how many electron-rich regions surround this sulfur atom. We have 1, 2, 3, 4 electron-rich regions, which means this ion has a tetrahedral electronic geometry. The ideal bond angle for this is 109.5 degrees. This would be the bond angle if the molecule was nonpolar. However, this ion has a lone pair with 3 bonds. This doesn't fit the criteria for nonpolarity that we've discussed in our previous lectures. This means that the actual bond angles here are going to be slightly less than 109.5 degrees. That makes the correct answer choice D. Problem 13 says, which of the following has a tetrahedral electronic geometry? I went ahead and drew out options A, B, C, and D. All we need to do is count the number of electron-rich regions that surround the central atom. If it's equal to 4, then it's going to have a tetrahedral electronic geometry. Here is the structure for answer choice A. The central atom is a sulfur, and it's surrounded by 1, 2, 3, 4 electron-rich regions. That means it's going to have an electronic geometry that is tetrahedral. It's in fact the correct answer, but we're still going to work through B, C, and D. B is shown right here. The central atom is also sulfur. It's surrounded by 1, 2, 3, 4, 5 electron-rich regions. That means it's going to have an electronic geometry of trigonal bipyramidal, which is not what we're looking for. Then we have C. In structure C, boron is the central atom, and it is surrounded by 1, 2, 3 electron-rich regions. That means its electronic geometry is going to be trigonal planar. This is also not what we're looking for. Finally, here we see the Lewis structure for answer choice D. Our central atom is surrounded by 1, 2, 3, 4, 5 electron-rich regions. Again, this is going to have an electronic geometry of trigonal bipyramidal, which is not what we're looking for. Again, the correct answer for 13 is A. Problem 14 says, which is the best Lewis structure for the ion IO4 - 1? Note the ordering of answer choices carefully. In order to solve this problem, we need to calculate the formal charge for every atom in each of these structures. The best Lewis structure is going to minimize formal charges while ensuring that the most electronegative atoms carry negative charges when applicable. The formula for calculating formal charge is valence electrons minus the number of non-bonding electrons plus the number of bonding electrons divided by 2. We're going to start with option A, and we're going to first calculate the formal charge of iodine, which is our central atom. Here, the number of valence electrons for iodine is going to be 7. Then we're going to subtract that from the number of non-bonding electrons, so lone pairs. There's no lone pairs on iodine here, so 0, plus the number of bonding electrons divided by 2. There are 4 single bonds. Each bond has 2 electrons for a total of 8 bonding electrons. That means what we have here is 7 minus 4, and that's equal to positive 3. So the charge on this central iodine is positive 3. Now we can figure out the formal charge of this oxygen. And what we notice is all 4 of these oxygens are equivalent. They form one single bond to the central atom, and they have 3 lone pairs. So once we calculate the formal charge on this oxygen, it's going to be the same for the other 3 as well. The number of valence electrons for oxygen is 6. We're going to subtract that from the number of non-bonding electrons, which is 6. And then that's going to be plus the number of bonding electrons. There's only one bond with 2 electrons, and that's divided by 2. So what we have here is 6 minus everything in the parentheses, which is 7. 6 minus 7 is equal to negative 1. So every oxygen atom here has a formal charge of negative 1, with the central atom having a formal charge of plus 3. Then we want to repeat the same process for each option. So I'm going to speed through this now that we know how to make these calculations. For the Lewis structure in answer choice B, iodine here is going to have a formal charge of plus 2. This oxygen is going to have a formal charge of 0. And every one of these 3 oxygens is going to have a formal charge of negative 1. Then we move into the Lewis structure shown in answer choice C. In this structure, iodine has a formal charge of plus 1. This oxygen and this oxygen, they both have a formal charge of 0, while these 2 oxygens have a formal charge of negative 1. Then in the Lewis structure shown in answer choice D, these 3 oxygens all have a formal charge of 0, and this oxygen has a formal charge of negative 1. And then iodine here actually has a formal charge of 0. So in structure D, there's only one formal charge. It's a negative 1, and it's associated with the oxygen atom. Very interesting. Now let's do our last one. Option E. In this case, all 3 oxygen atoms have a formal charge of 0, and the iodine has a formal charge of negative 1. So looking at these 5 options, the first thing we want to look for is a Lewis structure that minimizes formal charges. Answer choice D and E are the only ones that have one atom with one formal charge. So just based off of that, these 2 are top contenders for best Lewis structure. Then from there, to decide which one is better, we want to make sure that if there's a negative formal charge, we want it to be on the most electronegative atom. So these both have a single atom with a formal charge of negative 1. In D, that negative 1 formal charge is on oxygen, and in E, it's on iodine. We want it to be on oxygen because oxygen is more electronegative than iodine. So in fact, the best Lewis structure is going to be answer choice D. And that is because it is the Lewis structure with minimal formal charges, and it has that negative charge placed on the oxygen rather than on iodine. Let's move on to problem 15. Problem 15 says, which of the following is polar? Polarity arises when there is an uneven distribution of electron density. In order to determine whether a molecule is polar or not, we need to keep in mind our rules for nonpolarity. Anything outside of what these rules cover is going to be a polar molecule in this class. So the first trend for nonpolar molecules is when the central atom has no lone pairs and it's all bonded atoms that are identical. This is the simplest way for a molecule to be symmetrical and nonpolar. So answer choice C is a really good example of a nonpolar molecule. You have your central atom, which is a carbon, and it's bonded to the same atom type, and it has no lone pairs. This molecule is nonpolar. The same goes for answer choice B. Here we have a boron atom that's bonded to 3 fluorine atoms, and it has no lone pairs on that central atom. So this molecule is also nonpolar. The second trend for nonpolarity occurs when the central atom does have lone pairs, but they're arranged symmetrically. There's 2 subcases of this. The first subcase is when we have 5 total electron regions, where 3 of those electron regions are lone pairs. So answer choice D is a good example of this. We have xenon, that's the central atom. It's bonded to the same atom type. These 2 bonds are to the same atom type. And then the other 3 electron groups are lone pairs. This molecule is symmetric and nonpolar. The other subcase for this scenario or this trend is when a molecule has 6 total electron regions, and either 2 or 4 of those regions are lone pairs. That is going to make a molecule nonpolar. So just from those rules and scenarios, we were able to determine that B, C, and D are all nonpolar, and A is polar. So the correct answer for problem 15 is A. Problem 16 says, how many valid resonance structures with optimized formal charges can be drawn for the carbonate ion? To solve this problem, we first want to calculate the total number of valence electrons. Carbon contributes 4 valence electrons, and each oxygen contributes 6 valence electrons, giving us a total of 18 electrons. Since there's also a 2- charge, that means that there are 2 added electrons. So that gives us a total of 24 valence electrons. Then, to construct the Lewis structures, we want to place carbon in the center since it's less electronegative than oxygen. And then we'll have the 3 oxygen atoms surround the central carbon. Then we'll form single bonds between each oxygen and the central carbon. This accounts for 6 out of our 24 valence electrons. From there, we want to distribute the remaining electrons on the terminal atoms to ensure that they have a satisfied octet. So we're going to give each oxygen atom 3 lone pairs to make sure they satisfy their octet. Now, when we do that, we've accounted for all 24 valence electrons. But there's a problem. Our central carbon atom does not have a satisfied octet. So what we can do is we can take a lone pair from an oxygen atom and form a double bond. We can actually do this in any one location for each oxygen atom, which means we can draw a total of 3 resonance structures for the carbonate ion. That means the correct answer here is D. 17 says, how many of the following compounds are polar? Once again, we need to remember our rules for nonpolarity. Everything else that doesn't meet our rules for nonpolarity is going to be a polar molecule for this class. Now, the simplest way for a molecule to be symmetrical and nonpolar is if the central atom has no lone pairs and all bonded atoms are identical. That's exactly what we see for CH4. This carbon atom is bonded to fluorine atoms only, and there are no lone pairs on this carbon. So this molecule is non-polar. This compound is non-polar. Now, some other rules for non-polarity is that you can have a central atom that has lone pairs, but they need to be arranged symmetrically. A case for that, or one scenario for that, is a molecule that has 5 total electron regions. 3 of those are lone pairs, and the other 2 are bonds to the same atom type. Another one is when there's 6 electron regions, where either 2 or 4 of those electron regions are lone pairs, and the rest are bonds to the same atom type. Now, we don't see any of those cases in the other 3 molecules, meaning these are all polar molecules. So there is a total of 3 of these 4 compounds that are polar. Problem 18 says, place these in order of increasing bond angles. If a particular substance has more than one bond angle, use the smallest one. To rank these molecules in order of increasing bond angle, we need to consider their electronic geometry and how the presence of lone pairs can affect ideal bond angles. We're going to start with selenium difluoride. I've drawn the Lewis structure right here for selenium difluoride, and we notice that the central atom is surrounded by 4 electron-rich regions. That means its electronic geometry is tetrahedral. Tetrahedral electronic geometry has ideal bond angles of 109.5 degrees. However, this molecule is polar due to the presence of 2 lone pairs, and these 2 lone pairs have a repulsion that pushes the fluorine atoms closer together, and it gives a bond angle of less than 109.5 degrees. Next, let's look at beryllium chloride. I've drawn the Lewis structure right here, and we notice that beryllium is surrounded by 2 electron-rich regions. That means it has an electronic geometry that is linear, and there are no lone pairs on the central atom here. It's just bonded to the same atom type. That means it's nonpolar, and its bond angle is going to match the ideal bond angle for linear electronic geometry. That is 180 degrees. Next, we're going to look at the phosphite ion. We've drawn the Lewis structure here. The central atom is surrounded by 3 electron-rich regions, and it's bonded to the same atom type with no lone pairs on that central atom. That means this is nonpolar, and the bond angles are going to match the ideal bond angles for trigonal planar electronic geometry. That is 120 degrees. Finally, we look at our final one. We have arsenic as the central atom here. It's bonded to 4 bromine atoms, and then it has a single lone pair. The electronic geometry here is trigonal bipyramidal. But since it has a lone pair, this molecule is polar, which means the bond angles are going to deviate from the ideal values. In this molecular shape, the smallest bond angles occur between the equatorial and axial positions. That's going to be 90 degrees if it follows the ideal bond angles, but it doesn't since it's polar and it has that 1 lone pair. So it's going to be less than 90 degrees. Now we can rank these from smallest to largest bond angle. The smallest bond angle comes from this molecule right here. Then following that is going to be selenium difluoride. Then third is going to be our phosphite ion. And then finally, beryllium chloride. So this ordering matches answer choice D. Let's move on to problem 19. This problem says in the Lewis structure shown below for perchlorate ion, what is the formal charge on chlorine? Formal charge is calculated as the number of valence electrons minus non-bonding electrons plus bonding electrons divided by 2. Chlorine has 7 valence electrons because it's in group 17. Then in the given structure, chlorine has no lone pair, so it has 0 non-bonding electrons. It does, however, form a total of 6 bonds with oxygen atoms. So that means it contributes 12 bonding electrons since each bond has 2 electrons. So what we have here is 7 minus 6, and that is equal to positive 1. So the formal charge on chlorine here is going to be positive 1. Let's move on to problem 20. Problem 20 says, which molecule does not follow the octet rule for its best Lewis structure? To determine which molecule does not follow the octet rule, we can consider the 3 main exceptions that we learned. Our first exception deals with hypovalent elements. So elements like boron or beryllium, they can be stable with fewer than 8 electrons. However, none of our answer choices contain boron or beryllium. Our next exception is for hypervalent elements. So elements in period 3 or beyond, they can accommodate more than 8 electrons, so they don't always follow the octet rule. The only answer choice here that has an element in period 3 or beyond is answer choice A. Phosphorus is in period 3. However, in this particular option, pH 3, it actually follows the octet rule in this molecule. So this is not going to be the correct answer for which molecule does not follow the octet rule. Our third and final exception that we've covered is radicals. So radicals are molecules with an odd number of valence electrons, and they cannot have a complete octet for all atoms because of that. So what we can do now is try to figure out how many valence electrons do each of these options have? And if one of them has an odd number, then that's going to be a radical, and radicals do not follow the octet rule. So for pH 3, phosphorus has 5 valence electrons, and each hydrogen has 1, but there's a total of 3 hydrogens. So there are 8 valence electrons in pH 3. So that is not a radical. Then we can do carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6, and there are 2 of them. So this is going to give us 16 valence electrons. That's an even number, so it's not a radical. Then we have NO2. Nitrogen has 5 valence electrons. Oxygen has 6, and there are 2 of them. This gives us a total of 17 electrons. This is a radical because it has an odd number of electrons. Since one electron is not going to be paired, then nitrogen does not achieve a full octet, and that's exactly what we're looking for in this problem. Now let's still do answer choice D. Nitrogen has 5 valence electrons, and then each chlorine has 7, and there's a total of 3. This gives us 26 valence electrons. This is an even number, so it's not a radical. Again, answer choice C is a radical. It has an unpaired electron, so it does not follow the octet rule. Moving on to problem 21. How many of the following compounds would have a tetrahedral electronic geometry? To determine how many of these compounds have a tetrahedral electronic geometry, we need to count the total electron-rich regions around the central atom. We'll start with sulfur dichloride. Here we see the Lewis structure for sulfur dichloride, and we notice that the central atom is surrounded by 4 electron-rich regions. That means it has a tetrahedral electronic geometry. Next, we can work with the hydronium ion. I've drawn the Lewis structure here, and what we notice is that the oxygen atom is surrounded by 1, 2, 3, 4 electron-rich regions as well, and that means it also has a tetrahedral electronic geometry. Next, we have selenium tetrafluoride. When we draw out the Lewis structure for this compound, we notice that the central atom is surrounded by 5 electron-rich regions. So that's going to have a trigonal bipyramidal electronic geometry, not tetrahedral. And then finally, we have boron triiodide. And we notice that the central atom here has 3 electron-rich regions. So that means it has a trigonal planar electronic geometry. That is not what we're looking for. So, how many of the following compounds have a tetrahedral electronic geometry? The answer is going to be 2. Problem 22 says, which substance has the smallest bond angle? To determine which substance has the smallest bond angle, we need to analyze the electronic geometry and the effect of lone pairs on the central atom in each case. Let's start with answer choice A, the phosphide ion. I have the Lewis structure drawn here, and what we notice is that the central atom has 4 electron-rich regions surrounding it. That means it has an electronic geometry that's tetrahedral. The ideal bond angles for tetrahedral electronic geometry is 109.5 degrees. However, since this compound is polar from these 2 lone pairs, then the bond angles will actually deviate from the ideal values. So it's going to have bond angles below 109.5 degrees. Then moving on to answer choice B, we have beryllium hydride. I have the Lewis structure drawn here, and we notice that the central beryllium atom is surrounded by 2 electron-rich regions, which means its electronic geometry is linear. Since this molecule or this compound is nonpolar, it's going to adopt the ideal bond angle for a linear electronic geometry, and that is equal to 180 degrees. Then we have our methyl anion. The central atom here, the carbon, is surrounded by 4 electron-rich regions. So it also has a tetrahedral electronic geometry. However, since it's polar, due to the presence of this lone pair, the bond angle is going to deviate from the ideal bond angle of 109.5 degrees. It is in fact going to be less than that. Finally, we can take a look at tin for hydride. The central atom is surrounded by 4 electron-rich regions, and they are all the same atom type. In addition, there's no lone pairs on the central atom, so the electronic geometry is tetrahedral, and this molecule is nonpolar, so it follows the ideal bond angle for the tetrahedral shape. That is 109.5 degrees. Now, from our options, we have 2 that are below 109.5 degrees. So we want to compare these two, the phosphide ion and the methyl anion, to see which one has a smaller bond angle. Phosphide has 2 lone pairs, while the methyl anion has 1 lone pair. The ion with more lone pairs is going to experience more lone pair repulsions, which is going to result in smaller bond angles. So our phosphide ion is going to have the smallest bond angle. So the correct answer is A. Problem 23 says, which of the following substances is predicted to have a seesaw molecular geometry? For a substance to have a seesaw molecular shape, it needs to have 5 electron-rich regions where one of them is a lone pair. So I've gone ahead and drawn the Lewis structure for chlorine, tetrafluoride cation, for xenon tetrafluoride, for ammonia, and for chloromethane. And looking at the Lewis structures for these 4 substances, we notice that chlorine tetrafluoride cation has 5 electron-rich regions where one of them is a lone pair. So it will have a seesaw molecular shape, and the correct answer here is A. Problem 24 says, draw a molecular orbital diagram for dicarbon. What is the lowest unoccupied molecular orbital? For dicarbon, we need to remember that the pi bonding orbitals are lower in energy than the sigma bonding orbitals. So, keeping that in mind, this is the molecular orbital diagram that we want to fill for dicarbon. Each carbon atom has 6 electrons. So that means we have a total of 12 electrons that we want to distribute into the appropriate molecular orbitals. We're going to start with the 1s molecular orbitals. Here we have a total of 4 electrons. 2 will be placed in the sigma 1s bonding orbital, and the other 2 in the sigma star 1s anti-bonding orbital. Then we move to 2s. Here we have 4 electrons to distribute. 2 go into the sigma 2s bonding orbital, and the other 2 go into the sigma star 2s anti-bonding orbital. Finally, we make it to 2p. We have a total of 4 electrons to distribute. We're going to place them in the pi 2p bonding orbitals. Now, the ultimate question is to figure out what is the lowest unoccupied molecular orbital. So this is the molecular orbital that is next in energy above the highest occupied molecular orbital. For dicarbon, that is going to be the sigma 2p bonding orbital. So the correct answer here is going to be answer choice A. Problem 25 says, using molecular orbital theory, determine how many unpaired electrons di-boron anion has. Is it paramagnetic or diamagnetic? Each boron atom has 5 electrons. So we have a total of 10 electrons to distribute in molecular orbitals. However, this is an anion, so it has gained an extra electron that we need to accommodate and account for. So, with that in mind, let's go ahead and distribute these electrons in their appropriate molecular orbitals. We start with 1s. We have a total of 4 electrons. 2 of them will be placed in the sigma 1s bonding orbital, and the other 2 will be placed in the sigma 1s anti-bonding orbital. Then we move to 2s. We also have 4 electrons to distribute here. We're going to place 2 in the sigma 2s bonding orbital, and then the other 2 in the sigma star 2s anti-bonding orbital. Finally, we've made it to 2p, where there are 3 electrons for us to distribute. We're going to place them in the pi 2p bonding orbitals. From here, we notice that there is 1 unpaired electron. This makes di-boron, the anion, paramagnetic because unpaired electrons create magnetic properties. So the correct answer for 25 is going to be D. There is one unpaired electron, and it is going to be paramagnetic. Let's move on to problem 26. Problem 26 says, using molecular orbital theory, determine the bond order for diboron anion. So to determine the bond order, we just need to look at the valence electrons, which are going to be in the 2s and 2p orbitals. And we want to go ahead and count the number of bonding electrons and the number of anti-bonding electrons. We are going to take the difference between those two values and divide by 2 to get the bond order. Here we have 2, 4, 5 bonding electrons and 2 anti-bonding electrons. So 5 minus 2 divided by 2 is going to give us the bond order, and that's going to be equal to 1.5. So the correct answer here is going to be B. Problem 27 says, using molecular orbital theory, predict which has the longest bond. Bond length is inversely related to bond order. So the higher the bond order, the shorter and stronger the bond. One of the easiest ways to quickly determine bond order for diatomic molecules is by recognizing that bond order is directly related to the total number of electrons in the molecule. We can use a simple reference table like this one, which lists the bond orders for common diatomic species based on their electron count. To use this trick, simply count the total number of electrons in the molecule and find where it falls in the table. If the number of electrons is exactly one of the listed values, then you can directly read the bond order. If the number falls between two values, then the bond order will be the average of the two. So let's work through our options. Here we have dicarbon. Each carbon atom has 6 electrons, so dicarbon has a total of 12 electrons. The bond order for that is going to be 2. Then here we have dicarbon, but it's an anion. It's gained an electron. So now it has 13 electrons. 13 falls right in between 12 and 14. So we want to find the average of 2 and 3. That's going to be 2.5. Then we can look at dinitrogen. Dinitrogen has a total of 14 electrons, 7 from each nitrogen. If we look at our table, we'll see that for 14 electrons, the bond order is going to be 3. And then for dinitrogen, that's an anion that has gained an extra electron. 15 is right between 14 and 16. So the bond order is going to be an average of 3 and 2, and that is going to be equal to 2.5. Now, which one of these has the longest bond? The longest bond is going to be associated with the lowest bond order, which is going to be 2. So answer choice A. Finally, our last and final problem says, what is the HOMO, so the highest occupied molecular orbital for difluorine? For difluorine, the sigma 2p bonding orbital is going to be lower in energy than the pi 2p bonding orbital. So when you draw out your molecular diagram, you want to make sure that you remember that so you can properly answer this problem. From there, we know that each fluorine atom has a total of 9 electrons. So with difluorine, we have 18 electrons to distribute. Let's start at 1s. Here we have a total of 4 electrons. We're going to put 2 in the sigma 1s bonding orbital. And then we're going to place the other 2 in the sigma star 1s antibonding orbital. Then we'll move to 2s. Here we also have 4 electrons to distribute. We'll put 2 in the sigma 2s bonding orbital and the other 2 in the sigma star antibonding orbital. Now we move into 2p. Here we have a total of 2, 4, 6, 8, 10 electrons to distribute. We'll place 2 in the sigma 2p bonding orbital. We'll place 4 in the pi 2p bonding orbitals. And then we'll place the remaining 4 in the pi star 2p antibonding orbital. Now, this problem is asking us for the highest occupied molecular orbitals. That's going to be our pi star 2p antibonding orbital. So the correct answer here is going to be C. And with that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.